Hi everybody. Okay, well, camera's on. So here we go. We are starting on chapter 3, and this chapter is short, which probably is good news to you. And some of it is a kind of a repeat of what we've already talked about when we've discussed matter a little bit. But this chapter specifically is going to focus on the atom. And so a lot of it is going to be history, models basically, like who, figured out what part, kind of where we are now in terms of the model that we use of the atom. And then also we'll, get to the basics, what the atom's made of. So starting off with the atomic models. We're going to go back again to the ancient Greeks and just again, kind of as a review, talk about the two main atomic models at that time, which again were not anything that had been experimented on or that people really had any type of technology that would help them figure this out. These were more just ideas. And so our first one was a man named Democritus. I have a picture of like his bust up there, up above me, wherever that is. Let me point the right direction. There we go. And he, along with another man named Leucippus, had said that matter exists as very small particles. These particles can't be seen by people, and we can't get any smaller. They can't be divided any further. He called these particles atomus. And that was the Greek word for indivisible. So that was the first theory. It should sound very familiar to you. And then the second one was an idea that was supported mainly by a man named Aristotle, or as far as we know, a man named Aristotle. And he said that matter consisted or existed as a continuum, and it was continuous, and it was something that could be divided infinitely. So those were the two big ones, and well, my question down there we'll talk about when we get to class. But those two were the big theories of the time, and they kind of hung on for a long time until dun 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 we get to a man named John Dalton. There he is. He's thinking very deeply, obviously, and he was the first one to be credited with with what we call the first atomic theory. And so he, based on what he had studied just in lab situations, he had isolated certain elements by this point. He was a chemist. He was a smart guy, and so he came up with these 5 points to his atomic theory. And he said, first of all, elements are made of atoms. And then he went on to kind of discuss atoms, and he took this from part of what Democritus and Leucippus had said. Atoms are indivisible and cannot be destroyed. Now we obviously know that there are some things we know that he didn't, and so that statement is actually not true, but he didn't know that based on technology. Third point, he said that atoms of an element are all alike. So what he was saying there is if he had a handful of silver, because it's all the same substance, all the same element, then all the atoms would be alike. And then he said, in kind of, in contrast to that, atoms of one element are different from the atoms of all other elements, especially when you look at their masses. And so now he's saying, okay, if I have a handful of silver, in my other hand I have a handful of iron, then I have two distinct different elements, and then not only that, their atoms are very distinctly different, particularly because of their weight. And then he said atoms combine chemically, remember that will form a compound, in small whole number ratios. And we've talked about this several times already. Remember, kind of our big example of this is H2O. So, H2O, H2O. Wow, why is my pen writing so weird? I must have picked a funny pen. Anyway, it was the idea that, it's always water as long as that ratio stays the same. And so as long as I have two H's and one O, then I know that I am dealing with water. And other compounds act the same exact way. And so as long as my ratio is correct, then I know that I have the same compound all the time. But then also, specifically to him, they're small whole number ratios. So you can't have half an atom or, anything like that in a compound. So that's John Dalton, kind of the first person to experiment, I guess you could say, to figure some of this stuff out. Now, notice if you were looking at the dates, notice this is almost 100 years, or actually a little over 100 years later. So we have these atoms. So John Dalton told us we have atoms. And so in the time between the first atomic theory and now the discovery of the electron, in that 100 years or so, technology was rapidly changing. Electricity, of course, became a thing, and we started figuring out different uses and different pieces of equipment, I guess that you could say, that would lead to further discoveries. So one law that had been written down, which we all kind of know, like we know this, the law of electrostatic charges tells us that opposite charges attract and that same charges repel. You know this just because you have played with magnets before, and so you know two magnets will stick together, the positive end to the negative end. But then if you try and put the two positive ends of a magnet together, you know how they do that kind of funny thing where they don't want to touch each other, they're repelling each other. So this was a documented law at this point. And then also somewhere in that time frame, they had invented what we call a Crookes tube, and that's a picture of it down here at the bottom. So here is the Crookes tube, and so it's at one end. It's not, the picture's not super clear, but at one end down here, a power source is being applied. So he's got a little, there's like a little probe thing almost, and so electricity is running through there, and then inside that tube is a sample of a gas, and it is being energized by that power source. So in this tube, you will see a visible beam, and the outside of the tube is just glass, but if you on the outside produce a magnetic field with magnets, obviously, or electric fields, and then you can change the path of that beam of light. Excuse me, not light. It's not light. It's actually negative particles. So here we go. So now the big deal about this. So the very handsome man there, his name is Joseph John Thomson. I've always learned him as JJ. So I just call him JJ. You know, we're close. Anyway, he used this Crookes tube and he looked at those cathode rays, which is that visible beam, and he determined that they were made of, or that there were a very strong presence of negative particles. And he knew this because it would, if he put a positive, if you put positive down on this side of the tube, if we're talking about magnets, and negative up here, that doesn't show up super well in my picture, then that beam of particles that he would see would bend down towards the positive, because again, electrostatic charges, opposites attract and same charges repel. And so he knew that because it was attracted to the positive side, that he had negative particles. And he's, again, another smart guy. He did some math and he calculated that these particles were very small. It's hard for me to say for some reason, 1/1800th of the mass of a hydrogen atom. So as you know, atoms are small, and so if you have 1 over 1,800th of that, then you have a very, very small particle indeed. And so he was the first person to kind of dispute the idea from Dalton that atoms are indivisible, because he said, okay, I know what an atom is, and here's a little part inside it. He actually called those little particles corpuscles. At some point, that word was later changed to electrons, which is what we know today. Okay, so now our friend JJ, he said that we know atoms are neutral because they're not attracted either way until you energize them, until we can kind of really watch them. So he said that these negative electrons, he also called them corpuscles probably, were embedded in a positive matrix. And he called this, famously, the plum pudding model, because it reminded him of this traditional Christmas pudding. Pudding just basically means dessert of some sort in this context. And so here's a picture. Here's the Christmas plum pudding. Looks very appetizing. And then here is a picture of his model to the side. And so the kind of the brown part is the positively charged material. And then the kind of little black circles with the negative signs in them, of course, those are the electrons. Okay, so now we've changed, that was our first change to the atomic model, going from this small indivisible neutral substance or thing, I guess, to now we have a negative part. And so then they started kind of trying to argue a little bit, probably, and kind of trying to figure out, okay, how's this negative part really go in there? So our next scientist is a Japanese man named Hontaro. I'm sorry, so sorry. Is Hontaro Nagaoka. And there's a picture of him. And so this was, again, the early 19th century. He didn't, and I don't know the background, honestly, he didn't agree with Thomson about the negative particles being embedded in the positive matrix. And so I don't know exactly what his experiment consisted of, but he proposed the Saturn model, and he said that the electrons were orbiting a huge positive center, and that the electrons were moving in kind of a flat ring, and so it looked like what we picture the planet Saturn looking like. And so in my little drawing there, the purple in the middle is all the positive stuff, and then the green around it is where the electrons were. So he wasn't disputing the idea of electrons. He was kind of tweaking where the electrons were. Okay, so now here's our next guy, and he is probably the big one. Ernest Rutherford. There he is. He is a New Zealander. He performed what is arguably the most often repeated, most famous, most informative experiment ever in the history of ever. Like, he's a rock star. Like, this is the guy. And it was a pretty straightforward experiment. He took gold foil, and remember, gold is malleable, so he rolled it into this very thin sheet, like as thin as he could make it. Take like what you know about aluminum foil and make it 100 times thinner. Like, it was crazy thin. And then he took alpha particles, which we'll talk about in a future chapter, but alpha particles are basically like helium atoms, very large positive particles. And he shot them, basically had this particle emitter. So it's similar to maybe like an X-ray machine for us. Anyway, and he shot these particles at this gold foil. On the other side of the gold foil, he had like fluorescent screen or like X-ray screen. And so because the alpha particles contained energy, they would make a mark, basically like a little light point where they hit. So he set this all up, and his hypothesis was that the alpha particles would just pass right through the foil. He was pretty convinced that atoms had a lot of empty space, and so he figured they would just go right on through. And what he saw was that was pretty much the case. He saw that most of the atoms did just pass through. So that was the first one. So most did pass through. So say if he was shooting like 100 alpha particles, like 95 of them went through. No problem, straight through. Then he noticed, because he could see kind of where they went, when they hit the fluorescent screen, he noticed that some of them went through, but they were kind of off at an angle. So they didn't go straight through. Something in there kind of made them veer off course a little bit. And so out of our 100, remember 95 went straight through, 4 went through at an angle. And, this is approximate. And then he noticed one out of every 100 didn't make it through, and they would bounce back from the foil. And he set it up kind of in a circle, and I'll show you a picture on the next slide, kind of what his experiment looked like. But some of them just bounced straight back. They didn't even make it through. And so he did this experiment, he shot thousands of alpha particles through this gold foil, and he proposed what we now know as the nuclear model. And it looks familiar to you because we use it pretty much. And he said that an atom has a very small, dense positive nucleus. So that's this dot here in the middle. So there's a small, dense positive nucleus, and it is surrounded by these negative electrons. Those are the red dots over there. And he knew that the middle was positive because alpha particles are positive. So he knew at some point that one that didn't go through, the one that bounced backwards, hit something that repelled it. And so he knew that electrostatic charges, that law tells us that if it's two of the same charge, then they will repel each other. So he knew it was positive. He knew that it was very small because it didn't happen, they didn't come in contact very often. And then remember that JJ and Honturo had already told us, okay, we've got these negative electrons in there. Well, if they are that small, which JJ had calculated for us, then this large alpha particle wouldn't be phased by them at all. They would just kind of pass right through it just because of momentum. So this was Rutherford's nuclear model, and it has stood the test of time. Like I said before, this experiment has been repeated, I don't even know the number of times, but it has always gotten consistently the same results as Rutherford did the very first time that he did it. So huge deal. I mean, like, if you're a science nerd such as myself, then you would be really impressed by this. It just is amazing that he did this. Okay, so here's kind of what his setup looked like. So here is his radioactive source. So this is the alpha particles. So here's where our alpha particles are coming from. Okay, and so they are shooting out, so they're going this way. So here's that gold foil, super thin. You could see through it. And notice that most of them just go straight on through. There's no, it's like there's nothing even there. They just hit straight on through. And then notice that you have these two, at least in this picture, these two that go off at angles. Those are two particles that came very close to the nucleus. So if you have the nucleus here, let me get my hand in the screen, and this this alpha particle is coming towards it, if it doesn't hit it straight on, but it's close, then it will kind of veer off. So it won't keep going in a straight line, but they'll push each other away. Boy, my hands look really huge in that little screen, don't they? Anyway, and so that's where he saw those angles being produced. And then every once in a while, you're 1 out of 100, whatever the numbers are, you get this one. So you get this guy where he just bounces straight backwards. And that's where you do have a head-on collision straight on so that it bounces backwards. And so anyway, he kept meticulous records of this. People have done this experiment since that time, have kept records of this. Anyway, it's phenomenal that that he did this, and it is amazing and a very good indication that we know what we're talking about when we say an atom has a small, dense, positive nucleus and a lot of space around it. Okay, so I know he had kind of geek out over Rutherford. He's kind of awesome. Anyway, so moving on from there, we actually get to more of a modern atomic model, even though it wasn't that much later. We have quantum mechanics kind of coming into the picture here. We're not going to go into all of that because I'm not smart enough to teach it to you probably in a way that is is good. So, but it is a physics-based idea that tells us where electrons are, what is happening with the matter and energy at these atomic levels and even at the subatomic levels, specifically the electrons. So we have a guy named Niels Bohr. I believe he was Danish. Anyway, he, I think, also was a student or worked with Rutherford. I should probably learn my history on this. But anyway, he did an experiment where he heated elements to very high temperatures, gave them a lot of kinetic energy. Remember, we've talked about that. And then he observed each electron's emission spectrum, which is basically the colors that they give off. And he not only noticed, okay, first off, they give off colors, which is pretty cool, but he noticed that each was unique to the element. So every element that he tested, and we didn't have them all then, our periodic table wasn't filled in at that point, but they each had very specific color bands. And so you guys have all probably heard of, remember Roy G. Biv? Roy G. Biv, oops. So that's, the color spectrum, the colors of the rainbow. So what he would see with different elements were just certain bands of color. So he might not see all of the colors, but he might see the orange and the green and the blue, or different combinations. And so every element was different. And he associated that as a physics person with energy levels. colors on the visible light spectrum, the RHEVIV, they have different energy waves that are associated with them. Red has lower energy, violet has higher energy. But anyway, based on these colors that he was seeing, and he said that electrons are not moving randomly, which was something that Rutherford did say, but in very distinctive energy levels that he called orbits. And that when they move up to a different energy level, because they've gained energy or heat because of his experiment, they're not really supposed to be there, so that makes them unstable. So they instantly move back to where they should be, but then all that extra energy that they had, they have to release it. And that's what we see as color. And so that's what he was seeing. And so he was able to say, okay, that one gave off red, which means that was a very low energy movement. So it didn't take a lot of energy. That other one was maybe blue or indigo. So there was more energy. It's a bigger jump between those two orbits. And so he was able to say that the energy was very specific between energy levels, and he called this quantums, or he called these amounts of energy quantums. And he said they were quantum leaping, which is an old TV show. Back when I was probably your age, this was a TV show, which was kind of cool. And I actually saw that there's going to be a new one coming out. So not the same thing, but it's based on these words essentially. But anyway, so instead of kind of the randomness of the electrons that we saw with Rutherford's drawing a few slides ago, Bohr's model has very distinctive, very organized looking energy levels. Okay, so then not that much later, more physics were applied. Several men worked on what we now know as the quantum mechanical model. And they said, okay, there are energy levels. Their energy level, and the electrons are in these orbitals, these orbits that Niels Bohr had already told us about. But they weren't quite as, like circular, not quite as neat looking as Bohr's model proposed. And that was probably because he was looking at very simple atoms, just because of, the experiment and also kind of what we had access to. But the men who worked on this one, again, physics background, lots of math involved, they came up with the idea that the electrons were, depending on how many electrons, depending on the size of the atom, were in all of these random shapes. And so that red circle up top, that's a low energy, up there close to the nucleus. And then notice that even though they're kind of different colors, the next one that is yellow and orange, they proposed that it kind of moved around that one, kind of like a figure 8. So electrons were moving kind of in different points. I'm not even trying to draw on the rest of them because it gets more confusing. But they have more kind of areas where they move through and kind of move around the nucleus, which is in kind of the center of all of those points. And so when you see an actual atom with all of those orbits kind of fused together around the nucleus, the electrons are just kind of all over the place. And so this model is still, almost 100 years later, the most workable version that we have of the atomic model. Even if with technology improving, even with our abilities to see more and all that kind of stuff improving, these guys got it right, that long ago. And again, even if you don't like this, even though if you don't even understand what I'm talking about right now, please be impressed with the work that was done, the abilities that these men had to figure out some of this stuff and figure out probably just the tip of the iceberg and the complexities of the things that God made. It's just awesome. Okay, anyway, moving on. All right, so now atomic structure. This should be pretty familiar to you, the parts of the atom. So now we're to these subatomic particles. So remember, this was the part of Dalton's model, or excuse me, atomic theory that we didn't really know yet. So people have found these different parts. And so we've got electrons, protons, neutrons. There are actually smaller parts than that. We're not going to worry about those this year. But we do have these three that you're probably pretty familiar with. Electrons are the smallest. They have a calculated mass of 9.1094 times 10 to the negative 31st kilograms. So notice the negative. So that would be 30 zeros in front of that 9 if we took it out of scientific notation. Negative charge, figured that out because they're attracted to a positive. Electrons, we now know, are responsible for the chemical properties of atoms, specifically and most importantly, how they bond with other atoms. And last but not least, they're located outside of that nucleus. Then we have the proton. Notice, I mean, it's still really small, but notice it's bigger than the electron, 1.6726 times 10 to the negative 27th kilogram. So that'd be 26 zeros in front of that 1. So it's super tiny, but still quite a bit bigger than the electron. Has a positive charge. It's inside the nucleus. And then the number of protons. If you know how many protons an atom has, then you know what element it is. And we'll talk about that in just a second. And then the neutrons. Very similar in mass to the protons. So 1.6749 times 10 to the negative 27th. No charge, hence neutron for neutral. They're also inside the nucleus. It's believed they are in there just to kind of buffer between all the positive protons so that the protons can still be together but not repelling each other in that little nucleus. These guys were discovered by a man named James Chadwick. We'll talk about him more actually when you guys get into chemistry in a couple of years. But anyway, there's a model. Now notice it is drawn more like a Bohr model. That's just for simplicity's sake, because if we tried to do the quantum mechanic model, it would be confusing. So anyway, so you've got the 3 parts, and yeah, you know this one. Okay, so now some of the properties of atoms. So first off, atomic number. This is the unique number of protons that an atom contains. So this is the positive charges. It's always a whole number. If we're talking about a neutral atom, then it is also the number of electrons, and we'll talk more about that. And on our periodic table, the numbers in the upper right corner, and that's, you know, every periodic table is a bit different, but in ours, in the upper right corner, notice they're all whole numbers. That's the number of protons. We call that the atomic number. If that number changes, then I have moved on to a different element. Okay, so this is the number that identifies what element you have. Now, mass number is the total particles in the nucleus, and so this includes the protons and the neutrons. So you're adding 2 things together to get the mass number. This leads us to the concept of isotopes. Atoms of the same element can have a different number of neutrons. As long as the protons stay the same, the neutrons can change in any way that they want to. It will still be the same element, but it will be an isotope of that element. Typically, an element has, you know, in nature, and we always kind of discuss the naturally occurring isotopes, anywhere from 2 isotopes to, you know, 5 or more. You know, it just kind of depends on the element itself. The isotopes can be very different. For example, carbon 12 is the building block of all living things. Like your cells contain carbon 12. And on the other hand, carbon 14 is a very highly radioactive form of carbon that you wouldn't want inside you. And so anyway, the presence of a different number of neutrons, for whatever reason, totally changes the characteristics of that element. So anyway, so those are isotopes. Now, when you're talking about isotopes, or when you're writing them, there's typically a very specific format used, or actually two possible formats, and it always involves at least the mass number and sometimes the atomic number. So the first form is more kind of like the long version. You have the element name and the mass number. So for example, if I'm talking about carbon that has 6 protons and 6 neutrons, I write that as the word carbon dash 12. The 12 is because I've added the 6 protons and the 6 neutrons. So that's one format. The other one is kind of more the shorthand, is where you have the element symbol, and it has the mass number on the top, and the and so that's what I'm talking about right here. Has the mass number on top, so that's the 12. And then the atomic number on the bottom, that's the number of protons, or it's the number that you could look for on the periodic table. So if you see that 12 over the 6, that's the mass number over the atomic number over the number of protons. So they're talking about the same thing, it's just kind of a different, depending on kind of what you're doing really, on which format you would use. Okay, so now we've got isotopes. You have a different number of neutrons, same atom. Ions are when you have still the same number of protons, because you can't change that, but you change the number of electrons so that now our protons and electrons are unequal. The only way that you can form an ion is to change the electrons. Remember, you change the protons, it's a whole new element. So if I have what is called an anion, this is the negative form of an ion. It is negative because of electrons being gained. So if I gain something negative, so if I'm saying plus minus 1, it becomes minus 1. It's kind of, it's a math rule. So for example, chlorine in nature typically is a -1 anion. It has 17 protons. It's number 17 on the periodic table. And it has gained 1 electron. So now I have 17 protons and 18 electrons. When it was neutral, remember, it had 17 electrons. So now I have positive 17 and minus 18. That's where my -1 comes from. Then you also, on the other hand, have cations. Cations are a positive form of an ion, and this is because electrons have been lost. So this is, this is me saying a minus 1 is a positive 1. So sodium tends to lose 1 electron naturally. So sodium is number 11 on the periodic table. That means it has 11 protons. And then if it loses 1 electron from its original 11 when it was neutral, then it has 10 electrons. So if I have positive 11 and minus 10, I get positive 1. Okay. And we'll talk way more about that and kind of why those things were, what the point, I guess, is of that. But that's an anion and a cation. All right, last thing, atomic mass. So atomic mass is defined as the weighted average of the masses of all naturally occurring isotopes for an element. So the SI unit for this is atomic mass unit, AMUs, and the amount, or what it's worth, I guess, basically 1 unit is approximately the mass of 1 proton or 1 neutron. So we're not talking grams, although a lot of times it is kind of converted that way for other reasons, but that's what we're talking about when we're talking about AMUs, is a proton or a neutron. The weighted part. So what does that mean? You may have heard this before, like your grade, your average in each class is weighted. 60% is tests, 40% is daily work. That's a weighted average, which means your tests are worth more than your daily work. So now, in terms of atomic mass, and I have an example here. So if I have carbon, good old carbon again, has 2 stable atoms. Carbon-12, we already mentioned, and then a form of carbon-13. So out in nature, if I went out and found a good sample of those 2 carbon isotopes, and kind of divvied them out, kind of figured out percentages, the 98.93% of what I found was carbon-12, whereas 1.07% is carbon-13. So I'd have a big old pile of carbon-12, kind of a little pile of carbon-13. Okay, so that's what I've got. So now, if I want to know the weighted average, I would take the percent as a decimal, which means I move my decimal 2 places to the left, and I would multiply it by that mass number. So I'd have 0.9893 times 12 plus 0.0107 times 13, and I'd add those 2 together. And when you do that, you get 12.01. So if you look at our periodic table, or if you look at one online somewhere, the bottom number, or the other number in the square, depending on the format, is the weighted average. So the known natural stable isotopes of that element have been gathered, have been counted, have been put into percentages, and then they have followed that math that I just did. And we'll do some more practice on this, but I want you to know kind of where it comes from. Okay, that is chapter 3. I think I talked a long time. but I hope you enjoyed it.